Okay. Again, thank you to all who have decided to come to this last class before spring break. I appreciate you for not letting me lecture to an empty classroom. So, all right, so let's try to talk. I kind of narrowed down the topics for today just because I wasn't sure how many are going to be here, and I'm sure you all want to get out of here. So, but I'm guessing it'll still take longer than I expected. That's what always happens to me. But so instead of trying to cover everything that I discussed in the outline last time, I'll just try to talk about 2-qubit quantum gates because I think that's like such an important part of quantum computing, and we'll spend a lot of time on it. But we'll go over many examples, and hopefully that way you get a good sense of what they do. So that's mainly an outline, but I want to finish up a couple things from last time. So this was last class. We were trying to show the answer to. I think this is from last time. Thought I deleted this, but anyway. So the last time we did the Ket algebra notation, and I showed you how if I give you a gate, for example, one which says operate with H on the left qubit and X on the right qubit, we built up by taking H tensor X and we operated it on 0, 0, 0, 1, 1, 0, 1, 1. And we saw that the column vector, or equivalently, whatever we get from that state, makes up the columns for this matrix. Do you remember that? That was only last class, so please. And then I said I wanted you to go back and check with matrix algebra, which means you take X and H, the two gates, this is the quantum circuit representation, right? Because H is acting on the bottom qubit, the left qubit, and X on the right qubit. So the right qubit is always the one on the top, the rightmost. And so X and H. And we just, as I said, we did it with Ket algebra, so to speak, but we can also do it with matrix algebra. I just wrote it down in code because it's simpler. You can also do it by hand, right? I mean, you should do it once each way so that you know for sure how to do these kind of tensor product manipulations, right? But here is the answer with Python code. First of all, you just write down the X gate, and then you take the Kronecker product with the H gate, which we've already defined many times, and we get exactly the same answer. So it's 1 over root 2 is outside, then this is 0, 1, 0, 1. Okay. You look here, that's 0, 1, 0, 1. Then the next one over the second column is 1, 0, 1, 0. And that is also 1, 0, 1, 0, and so on and so forth. Yeah, so we can see that we can get the matrix form of the gate by operating it on 0, 0, 0, 1, 1, 0, 1, 1, or by using the tensor product in this case when there are two tensor, when there are gates that can be constructed as single qubit operations on each individual qubit, then this is the gate output. Okay. Right, and we can do it in Quark as well. So let me show you that. Did I do that last time in the class? I can't remember. Anyway, all right. Let's if not, we'll redo it. Where is that? Okay, so there is the Quark simulation, and we wanted, what was it? H tensor X, right? So H on the left qubit and X. Now X, remember, also has the symbol, which is this plus sign, right? Because it takes the naught basically of the gate. So, and we can see now what that does to this output state. Sorry, let's put the output states. Let's go through the output states one by one. So that's 0, 0. And we see, as expected, it's going to flip the top state and the bottom state. It's going to create a plus state, basically, when we do 0, 0. But we can go through all the superpositions. So 0, this is 1, 0. Oops, that's the one annoying thing about code. I had to cycle through these states one after the other. Can't seem to just reset. Maybe there's a way. I don't know code well. Anyway, was it 0, 1? So we want the top qubit to be 1, the bottom qubit to be 0. And then again, as expected, we get plus over here, and then over here, we get that qubit has been turned off because 1 going into the X gate. And also remember this is tells you what the state is. Of course, it tells you in the block sphere representation. It also tells you in the 0, 0, 0, 1, 1, 0 representation, which is what we'll need when we discuss states that cannot be written down as product states. So this representation, we can almost use it to also read off what's going on, because it says here for the 0, 1 state, there's a 1 over root 2 on the 0, 0. So that's the top element in the column. And then there is another one on this state over here. So that's the 1, 0 state, and that also has a 1 over root 2. So in the column vector notation, remember 0, 0 is the top element. So that's a 1, right? 1 over root 2 is outside. So that's 1, 0, 1, 0. And of course, that's what we got for the second column in the matrix that we were just looking at. Yeah. Sorry, I don't have a way to switch back and forth between the two, PowerPoint and this. When you go back, you can verify for yourself. This is indeed the case. So let's go back to let's read out the 0, 0, 1 as well. So the 0, 0 matrix, the 0, 0 input state gives me, so for the top element, it's 0, right? That's 0, 0. That's this element over here. This box represents the output for the 0, 0 state. This box is for the 0, 1 state. And that has a 1 in it, basically, because of the 1 over root 2. It's a 50% probability to be in that state. And then similarly, the 1, 1 state has a 1 in it because it's 1 over root 2 times that state as well. So we can use this to construct the column vector by saying it's basically 0, 1, 0, 1. Does that make sense? What I'm saying from this? I don't know if I'm always. Let's switch this both to 1, 1, because that's an interesting case. Because as you see, so 1, 1, we know this will of course become 0, so that's no problem. But this one, you see, goes to the minus state, which of course on the block sphere is represented by the thing pointing along the minus x-axis. But look what it does also to this column, to this vector over here. Okay, so what you should think of, why is there a circle with an arrow or a line in it, is that's the complex number. So meaning if this was not just 1 or 0 or 1 over root 2, which are real numbers, right? If they're real numbers, they'll be along the real axis. So this one points along the real axis, telling you that this is a real number. Now, if it had a complex notation, then this would point somewhere off to the, in the complex plane. Remember, any complex number can be represented as x plus iy, which can also be written in the complex plane as r e to the I theta, right? So any complex number here will be represented along with some line or some, maybe it's simplest if I try an example here. So let's try an input here, which will make this, that won't work. Let's try that. Okay, yeah, now you can see, okay? So when I put an I state input over here, it's not in the computational basis, but I'm allowed to put in an I state. Well, H acting on an I state produces things along the block sphere, right, which are plus I and minus I, okay? And so H acting on I, gives me the minus I state, and you can see now what happened to that amplitude over there. You see that? It's now pointing not, the probability is still half to be found in this state or this state. So there's a 1 over root 2 in the outside, but there's a phase, e to the I theta, on each of those amplitudes. And you can see what the actual number is by going and mousing over and you see it's 0.5 plus 0.5i. So because there's a 0.5 plus 0.5i, this is pointing along at 45 degrees to the axis. Does that make sense what that notation is in that box over there? If not, we can go over it again. And you can verify that this is true once again, just by going back. Well, I mean, I put the code there, but we can also do it now, which is if instead of sending in the input 0, 0 or 0, 1, if I sent in this state into that matrix and calculated its output, then the output would be these states. Okay, along the 0, 0, there would be like a 1 over root 2 plus 1 over, or 1 half plus 1 half I in front of the 0, 0 state, and then the 0, 1, 0 state would have 1 half minus 1 half I. Okay. That would be the end. So you can check that. You have the matrix, try to put in the state and calculate the output with the matrix and check that that agrees with the quirk simulation. Okay. I advise, you should all check these things independently from on your own to make sure it all makes sense. Okay. So any questions about this? What this notation is and what these things are? These circles with that pointer. And we can do another example here. See. The minus I input again says it's 50% to be on because it's in the plus I state, and now you can see it's now switched that phase. Now this one is 0.5 plus 0.5i, the bottom one, and this one is 0.5 minus 0.5. Okay. So anyway, so it's worth playing with this a little on your own, making sure you understand those outputs. I personally, I'll check it with Python and then I'll quickly look at it on Quirk to make sure I didn't make some mistake in entering my from window. Let's see. Okay. Okay, so now so we've covered now the 1 qubit or single qubit quantum gates, meaning single qubit quantum gates are those where you build up bunches of, even if you have many qubits, the gate by itself, each of them act only on 1 qubit at a time. Okay. So 1 qubit, for instance, I could have shown you that entire circuit without the other qubit, and you could have, you would have known what the output was for each wire, what the output was going to be. But now we are going to come to a situation which is probably at the heart of quantum computing, which is the 2 qubit quantum gates. So yeah, so that's what I was just saying. So we can have gates where both qubits are affected at the same time. Okay, and we call these 2 qubit gates. Okay, and they're similar to binary logic gates. So you remember when we took A and B, 2 binary digits, say 0 and 1, we can construct AND gates or OR gates or NAND and NOT, NAND, NOR, XOR, etc. All these gates which require 2 inputs and the output is dependent on both inputs, right? Same idea here. We have 2 inputs and we want the output to be dependent on both the inputs. Okay, so the best way to illustrate these 2 qubit gates is just with the examples of what kinds of gates I'm talking about. And in particular, of course, I'm going to be focusing on the gates that have been shown to be important for quantum computing. There are, of course, an infinite set of gates I could write down, right? As by now, any unitary gate acting on the 2 qubits is a valid quantum gate, right? Any unitary matrix or unitary operation that I can write down that takes 4 column vectors, column vector of 4 numbers and puts out another 4 numbers. And as long as, if this is normalized and this is normalized, that's what I mean by unitary operation, right? Unitary gate. And we can check that it's a unitary gate by just taking U dagger U and checking that it's an identity matrix. So all of that stuff that we worked in in single qubit gates, all of that applies to our two qubits or higher dimensional qubits space. But the point is, we want to build up with like simple ones like AND or OR. But instead of that, we'll introduce probably the most important 2-qubit gate, which is called the C0 gate. Okay, so let's go through the C0 gate. What it does is a very simple thing to describe in words. So it inverts the right qubit if the left qubit is 1. And if the left qubit is 0, it doesn't touch the right qubit. So it leaves the right qubit alone. So we can illustrate it by simply looking at what it does to all the different basis states. So if I put in 0, 0, well, the left qubit is in 0, so nothing happens to the right qubit. Yes? If the left qubit is again 0, the right qubit is 1, the output is again 0, 1, because nothing happens to the right qubit. But what happens is if the left qubit is 1 and the right qubit is 0, I get a 1, 1. I've inverted the 0 on the right qubit. And same thing, if I have a 1, 1, I must invert the 1 to get a 0. Okay, so that is the C0 gate. And the left qubit then, as you can understand, is called the control qubit, because it controls what happens to the other qubit. So the other qubit, the right one, is called the target qubit. Make sense? Okay. So it's very simple to describe, very simple to write down in the basis states. Okay. So we can also be viewed as a quantum XOR gate. Why is that? Well, look back at what we just wrote down here in this table. So if I have an input 0, 0, and I write it as an output 0 plus 0 XOR 0. 0 XOR is just binary addition. Addition modulo 2. Remember that? All the way back in lecture 4 or something. So it's just, if I add 0 and 0, I'm going to get 0. 0 and 1, I'm going to get 1. Okay, 1 and 0, I'm going to get 1. 1 and 1 would give me 2, right? Like 1 plus 1 is 2. 2 in binary is 1, 0. But, because of either you can think of it as I drop that 1 or I do modulo 2, which means 2 modulo 2 is 0 because it gives me a 0 remainder. When I divide 2 by 2, I get a 0 remainder. So that's a 0 again on the right qubit. Okay, so that's what we mean by A modulo 2 addition or A XOR B for that second state, right? Everybody okay with this? Why this is A XOR B? Or A modulo 2 addition B, A plus B in modulo 2. That's a symbol, if you remember, for modulo 2 addition, and also XOR. Okay. So, yeah, that's just what I was trying to say. Control qubit is always unchanged. Target qubit is the XOR the 2. So it depends on the state of the first one. The output on the second one isn't independent of the first one, okay? Or the left one. Another way to think about the control NOT is because NOT and X gate are the same. Remember, we were just seeing that in the court simulation when I put the plus sign, the XOR sign, which is the X gate. The control NOT is also viewed as controlled X. Okay? Control X or control NOT, they're all the same in this picture. Okay? Okay, and the other thing that I want to, probably the most important point about C0, this is why it's so important and so useful and used all the time in quantum computing, is that it produces entanglement. Okay, if you think back to entanglement, remember we had states. Normally the states that we write down are tensor products of 0 and 0, or it could be like psi1 and psi2, where psi1 and psi2 are just general qubit states for qubit 1 and qubit 2. Okay, but entangled states are ones that I cannot write down, where they are, where I cannot write them as just a tensor product of the two individual qubits. So as an example, so if C0, for example, does not act just on 0, 0, but acts on plus 0, and how might I get a plus on this left qubit? Anybody have an idea how to go from 0 on the left qubit to a plus state? What gate can I use to do that? I want to go from 0 on the left qubit to a plus state. Yes? Excellent. Exactly. So if I have a Hadamard acting on the left qubit when it's in the state 0, I get a plus state. So then if I act with a C0 now between these two, then let's see what the action of C0 will be. We know what this plus is. Plus 0 is just 1 over root 2, 0, 0 plus 1, 0, right? The first qubit is in the 0 plus 1 state. Second qubit is in the 0 state. So it remains, it's still a product state. This state is still a product or separable state because the zero can be factored out, basically. But now let's look at what C naught does to this. Well, C naught acting on 0, 0 doesn't do anything, doesn't touch it, but C naught acting on 1, 0 inverts the 0 on the right qubit to be a 1. So this now becomes 1, 1. Okay. Now this state cannot be factored out. We proved this as a little theorem when we did it, that you cannot write this as the product of two separable or of two general qubit states. You remember that proof was, write it as a column vector, and then the product of the top two coefficients is never equal to the product of the middle two coefficients. And therefore, cannot be written as product state. Okay, let's do it with minus state. Okay, minus input on the first qubit and 0 on the right qubit. So this is just 0, 0 minus 1, 0. And following the exact same argument, this is now 0, 0 minus 1, 1. Okay, also an entangled state. Then we can go to, of course, input plus on the left qubit, 1 on the right qubit. I write this as 0, 1 now plus 1, 1, right? Exactly the same as this one, except that the right qubit is now a 1. C naught acting on 0, 1 again does nothing to the 1 qubit, right? To the right qubit is untouched, so that remains as 0, 1. But the right qubit, the second state here, the input is 1, 1, and the C naught acting on this 1, 1 state, it takes the left qubit and inverts the right qubit. So that's a 1 on the left qubit. So I get 0, 1 plus 1, 0. Okay. And finally, of course, if I send in C naught acting on the minus state and 1 here, by this everything is exactly the same as this one, except there's a minus sign. So you get 0, 1 minus 1, 0. These states are called the Bell states or EPR states. They are also called maximally entangled. Does anybody remember what I meant when I said maximally entangled? What is the definition of maximally entangled? Yes.
They store redundant information because once you measure one, you know the value of the other.
Exactly. Very good. So as soon as I measure one, the other state is 100% determined. We know exactly what that other state must be. Yes. Because of course, there are the more general superposition states, which we have taken examples of in the past. If you measure one qubit, yes, there's a collapse of the second qubit, but there may still be some superposition left behind in the second qubit. It may still be in some kind of, superposition state. Those are not maximally entangled. But Bell states are. Okay, Bell states or EPR states are, and in fact, there's a name or a notation that I want to introduce. I don't know if I introduced it. I may have written it down on the chalkboard, but I wanted to write it down here, which is the first state we wrote down in that on the previous slide, 0, 0 plus 1, 1 is given this symbol, capital phi plus. Okay. And 0, 0 minus 1, 1 is given the notation capital phi minus. Psi plus is given the notation 0, 1 plus 1, 0, the psi, capital psi plus. And then capital psi minus is 0, 1 minus 1, 0. So these are the maximally entangled states or Bell states. And it can be shown. Of course, we know that 0, 0, 0, 1, 1, 0, 1, 1 forms a complete basis set because every state in the 2 qubit space can be written as a superposition of them. It turns out that these 4 states also form a complete set, which you can show by taking these states and calculating the completeness relation of it. Okay. Completeness relation is, I'll take phi plus outer product with phi plus, phi minus with outer product with phi minus bra, psi plus with outer product of with its bra, and psi minus with its bra, and add them all together. You should get the identity matrix. Okay? And that will probably I'll assign that as a homework for the next couple of weeks or something. Not spring break. After that. Okay. All right. Any questions on this last thing here? Over here? These states are why C naught produces entanglement. Is that clear to everyone? Okay, and of course, we can find what the matrix must be for C naught by the exact same way that we did it for the HX gate or the HI gate or projection gate, etc. we follow the same procedure. We take C naught, we operate it on 0, 0. Okay. Well, we know that does nothing. It gives me back 0, 0. So what column vector is that? If I get back a 0, 0. Yes.
And I density matrix.
No, I'm just asking for the action on just this one.
Oh, okay. So 1, 0.
Yeah, exactly. 1 followed by 4 zeros, 3 zeros. Exactly. Okay, what about C naught acting on 0, 1 state? Anybody? What will be that column vector? Yeah, 0, 1 state. Because that's the next one, right? So if I have C naught on 0, 0, the next one I want to do is C naught on 0, 1. Everybody understand the procedure, right? Even if you don't immediately know the answer, you know what to do, right? I just want to make sure. If I give you some matrix and I tell you its action on the basis states, then you have to be able to construct the matrix for it. And that's why I want to make sure that everybody knows that procedure, what to do. Like the basic idea is you take C naught or any gate, whatever it is, you acted on 0, 0, acted on 0, 1, acted on 1, 1, 0, right? And then acted on 1, 1. Okay. And of course, you know the answer in terms of kets. This is just 0, 0, but we also can write that as a column vector, right? And that column vector, as we just said, is just 1, 0, 0, 0. Now, what will it do to 0, 1? Yes.
It also
Gives me?
it gives you 1, 0, 0, 1.
You think it's 1, 0, 0, 0 again?
No, I think it's 1, 0, 0.
1, 0, 0, 1. Ah. See.
I think.
Then, yes. This is good. Everybody agree with that? Yes.
I think it's 0, 1, 0, 0.
Exactly.
I think I see what he's using to kind of makes sense.
I had 0.
Good, good. So tell me what confused you. Why did you think it was 1, 0, 0, 1?
I thought that was
I'm sorry, I don't remember your name. Howard, yeah. Okay. Why did you think it was 1, 0, 0, 1?
yeah, that was the 0 state on top of the 1 state, but I don't see what that.
Huh? Say that again. I'm
So it was
sorry.
like the 0 state and then the 1 state underneath it.
Yeah.
That's what they said.
Oh, okay.
That's why I thought.
I see. Does everybody follow why it's 0, 1, 0, 0? Because remember, just like in the single qubit space, ket 0 was the column vectors 1, 0. And ket 1 was the column vector 0. Now we have 4 basis states: 0, 0, 0, 1, 1, 0, 1, 1, and we have chosen to write them from top to bottom. So whenever we get a 0, 0, we write a 1. Whenever we get a 0, 1, we write a 1 over in the second element. And if I get, obviously now hopefully the answer is clear, because if it was just 1, 0 here, I would get 0, 0, 0, 0, 0, 1, 0. But what does C naught acting on 1, 0 give me? Somebody else? Yes.
1, 1.
1, 1. Very good. Yes, and the person, I'm sorry, what's your name in the black? Lucas. Yeah, Lucas. So would you tell me what the column is? 0, 0, 0, 1. Excellent. And who wants to tell me what happens to C naught on 1, 1? Yes.
1, 0.
What's your name again?
I'm Ryan.
Ryan. Okay. 1, 0. Very good. And does somebody want to supply the column vector? Yes, you can do it.
Yeah,
Right.
0, 1, 0.
0, 0, 1, 0. Excellent. And now, if I want to write the matrix representation of C naught, all I do is take each of these column vectors and put them together. Okay. 1, 0, 0, 0. That's this first column vector over here, right? And then the next column vector is 0, 1, 0, 0. Third column vector is 0, 0, 0, 1. And the fourth one is 0, 0, 1, 0. Okay. And the nice thing is, if you stare at this for a little bit, you begin to see a pattern. You notice that this part is just an identity matrix, right? And this part is just an X gate. So it kind of will, start to see why it's a control X gate becomes a little bit more sort of obvious when you look at this matrix. Because this part is an X gate acting on the second qubit and this part, but they're not separate. They have to act together. We can't write this as the tensor product of identity times X. Okay. It's not identity times X because we already saw what that gate was in a previous example, and it wasn't this. Okay. So this is a new gate, it's a control X gate, and this is its matrix representation. So that's it. This is the standard technique for getting the operation of a gate and finding its matrix representation. So, and you now know this, so you can construct almost any gate you want with this notation. Okay, and I just wrote it down over here, exactly the same thing. 1001 up here and then 0110 down here. Okay. Now, what will happen when C naught acts on a general superposition? Okay, well, we can write it in two different ways. Okay. I should have just said that. Avoided this whole thing. Right. We can write this again using two forms, right? C naught acting on any general superposition. What's the most general superposition of the two qubit states? Yes. Forward.
A, B, C, D.
A, B, C, D. Just that, or in Kent algebra form? Can you tell me in Kent algebra form?
A 0 0
Yes.
plus B 0
Yes.
1.
Exactly. Plus C 1 0 and D, right? That's what you want to say. Very good. And now we know what C naught does on each of these states. So we just write it down. A C naught acting on 0 0 is just 0 0 plus B C naught acting on 0 1 is just 0 1 plus C acting, what is C naught acting on 1 0 is
1 1.
1 1. And then E is 1 0. Okay. So that is one way to write this down, but we can also write this down using the matrix form. So it's the matrix 1 0 0 0 0 1 0 0 0 0 0 1 0 0 1 0. Now I want to act this on this state written as a column vector, okay, which is just the column vector A, B, C, D. Okay. So let's verify that this gives me that superposition over there. So I take this row vector and I multiply it by the column vector, right? That's the first element in this output state. Okay. So what is that? Well, that's 1 times A and everything else is zeros. So this is just A. Okay, very good. Then same thing here. I take this row vector and I multiply through that column vector. I get B. And finally, the third one is I take this row vector, multiply it by this column vector. Hopefully you can all see, that'll give me D. Okay. Right, because it's the fourth element that has a 1 in this row. And here again, the last row has the third element as 1 and everything else zeros. So that gives me A, B, D, C, which is exactly what we wrote here too. So it's A, B, and then C though is in front of the 1 1 state, which would then put it down at the bottom, D on the 1 0 state. So if I wanted to be more careful to convert this, this is A 0 0 plus B 0 1 plus D 1 0 plus C 1 1. We always want to write the state in this way when we're comparing the two, because otherwise you'll be looking at the wrong coefficient for the state, right? So because it's written in the order of the decimal representation. So this is the number 0, this is the number 1, This is number 2, and that's the number 3 for the decimal representation. So we always write it in that order. A, B, D, C. Okay. So it's important to know the circuit symbol for this. This is so commonly used that we have to understand and know this at all times. So when we put this dot over here, this black dot, it means that this is a control qubit that affects the operation on this one. So it means that this qubit, and remember, because the left qubit was working as the control qubit, that's the one that's on the bottom, right? The control is on the bottom here because we wrote the left qubit as the control qubit. The one, if it's in a one state, then it inverts the top qubit because that's the right qubit. So the right qubit is the top state or the top wire here. So that's the one that gets inverted by the X gate or the binary addition gate, basically. And that is controlled by whether this bit, this wire is in the 0 or 1 state. That's what this notation is supposed to represent. Okay. And we can see it in Quirk as well. Right there. And so let me try this out. And you see this control little orange, this black circle. As soon as I put it there, it knows that I'm trying to draw a control between the left and the right qubit over there. And so let's work through that and make sure we follow that. Let's go through it again. The 0 zeros. So as expected, when it's an input is 0 0, the output is 0 0. Right? The left top element. If the input is 0 1, then as expected, the nothing happens. So this remains a 1. Okay. So 0 1, and this output is also 0 1. If you get confused about which is 0 1, you just mouse over there. And it tells you amplitude of 0 1 is 1. Now we have the element 1 0. Sorry, I should have remembered to. There it is. So now this is 1 0, and now we see 1 0. Well, the 1 passes through, that remains an on because 1 is a control qubit, nothing happens to it. But now the 0 state has got inverted to the 1 state. And that's why it appears now down here in this box, because that's a 1 1 amplitude. Okay. Again, to check, you can mouse over there, and that tells you the 1 1 amplitude. And finally, of course, when it's 1 1 input state, then the output is 1 0, and that is the box over there. Again, so, and now we can do what I said, which is I can just change this 1 to a plus state. You see that? When I change that to a plus state, now suddenly we have superpositions of these two states, which, if you remember, that was the 1 0 plus, 1 0, 1 0 plus 1 1 state. Okay. So the output is now in this entangled superposition. Okay. Okay, so you can play with that on your own. Stop this share. Oh, I'm sorry, I made a mistake, didn't I? That's not entangled, because the one that has to come in is this one right there. Now we're talking. So now you see now the block sphere representation, it doesn't know what to do, because as I've told you, there's no way to represent an entangled state on the individual blocks. Okay, so the individual block spheres, it just shows you like a circle at the center saying, oh, I don't know how to represent this on the individual block spheres. Okay, but on the 2 qubits, now it's, this one, 0 0 plus 1 1. 0 0 plus 1 1. And that's one of the Bell states, the first Bell state, 5 plus. Okay, and what else can be gleaned from this? you'll notice actually as we go through this that these Bell states will always appear as sort of diagonal or anti-diagonal pairs. Okay, let's go through them. It's fun. Okay, so plus and 0, let's make plus and 1. You see that? Now that became this diagonal over here in this box. Okay. And of course, if I make this a 0 again, that's that, but sorry, what is that? Yeah, this one is a minus now. Again, this is a diagonal in the same diagonal, but now see how this has switched over to its phase. That little pointer is pointing in the negative x direction. In the complex number, that's just because it's a minus sign along the real axis over there. Okay, and one now again, it's back to this this other diagonal. Again, these two are pointing in opposite directions. So saying that there's a minus sign of phase between. Everybody okay with this? What I was just saying? Okay. Questions? So one of the things I want to an important convention that I want to introduce is the labeling of the C naughts. Because you see we have two qubits and we can choose either the bottom wire, which is the left qubit, to be the control, or we can choose the top wire, which is the right qubit, to be the control. Okay. And so the notation is slightly, how do we write it down? I mean, on the circuit, it's very easy, right? I just switch the control to the top and the plus sign to the bottom instead of the way we had written it. But when we are writing it down on paper or in some protocol or something like that, it's helpful to know which one we want to use as the control and which qubit is the target. Okay? And the way that is done is this notation over here, C naught Ij is C naught with the qubit I as the control and qubit J as the target. So meaning if I write 1, 0, which is what we've been using so far, that is the left qubit is the control, the right qubit is the target. That is, the bottom wire is the control, the top wire is the target. That's that symbol that we just saw. Okay. But we now switch 0, 1. Okay. The 1 represents that's the control one. That's the one that we want to use to control the other one. Okay. So now the right qubit is the control and the left qubit is the target. Everybody okay with this convention? What it means? I'll show you in a minute what it is. So the two symbols will look different. So this is the one I just introduced, which is the bottom wire or left qubit is the control, right qubit, which is the top wire, is the target. And this symbol is the one I just now have newly introduced, which is C naught 0, 1. Okay. Again, that means that the right qubit, which is the topmost wire, is the control, and the bottom qubit or the bottom wire, which is the left qubit, is the target. Okay, that's the one that gets inverted depending on whether the right qubit is 0 or 1. Okay, so we have these two C naught gates and they are related to each other. Okay, so we have an identity. This is an important sort of circuit identity that we can use, and I will prove it to you in a minute. But the claim is that we'll write this first in the quantum circuit language. It's very compact, right? As you can see, it says that if I proceed the qubits, if I proceed this gate, which is the C naught 1, 0 gate or standard C naught, as I will call it from now on. Okay. So sometimes I might omit 1, 0 at the bottom. It just means it's the original one, the first one that I introduced, where the left qubit is the control and the right qubit is the target. So that qubit, if I sandwich it between a pair of Hadamard gates on the left and right qubits, then I claim that this is equivalent to having just a qubit with the control on the right qubit and the target as the left qubit. Okay, that's the claim. And in Ket algebra notation that says, remember, we always want to read the circuit. When we read the circuit from left to right, we have to write the matrices from right to left. Okay, so this is H tensor H, and then C naught 1, 0, and then H tensor H. Okay, That is the order of the operations. And that I claim is equal to C naught 0, 1. Okay. So first we will prove it using ket algebra. Okay. The proof will look a little bit long. You can see that linear algebra will be very quick because we know how to write H tensor H in linear algebra form. C naught we have written down in linear algebra, and we have written down, and we know H tensor H again. So in Python, it's just one line of code again. You just write down each or 3 lines. Maybe. You write down each matrix and you just find the multiplication, and Python will do it for you. But it's instructed to go through the ket algebra case. So the proof. So I want to do that way as well. Now I am going to differ from the proof given in your textbook, because I find that proof is kind of really tedious and hard to follow. Okay, so I'm not going to use that proof. I'm going to show you my proof of this, which may be the general proof or general way of proving these things. I don't know. Like, it's just the proof that I find the simplest, easiest way to do it. So I'm going to show you. It's still complicated enough that we'll have to go through it step by step. But I think it's a little simpler than the chain of algebra that's in your textbook. Okay, so this is my LHS, the left-hand side of that equation. That's my LHS. And the right-hand side is, of course, this is first of all, it probably behooves us to ask, and let's see. Well, okay, let me get through the first line of this proof and we'll discuss what's happening. Okay. So I'll put a space here for the RHS. The RHS is very simple to write down. Okay. So what the proof that I'm going to tell you about is a very simple idea. I know that any general qubit state in the 2-qubit space can be written as A times 0, 0 plus B times 0, 1 plus C times 1, 1, 0 plus D times 1, 1. So what I'm going to do is I'm going to take each of the individual basis states in that superposition, 0, 0. I'm going to see its action on through this left-hand side and on the right-hand side. And if the two are equivalent, my theorem is proved, right? Because any general state can be written as a superposition of those 4 basis states. So if this theorem is to be true, it has to be true for each of the individual components in that basis state. Okay. So we'll look at its action on each of the individual states, and if they are equal, then the theorem is also proved that way. Okay. So 0, 0, H tensor H acting on 0, 0. Well, that's just the states plus plus, right? Right? H acting on H will act on this, H will act on that. Both of them will give me plus plus state. Pretty okay with this so far? Which I'll now write down 1 over root 2, 0 plus 1, and 1 over root 2, 0 plus 1. Okay. And I'm omitting the tensors, but they're always to be understood. So that's just 1/2 0, 0 plus 1, 0 plus 0, 1 plus 1. Right? Equal weight of all 4 states. Now I need to act with C naught, which takes, depending on the left qubit, will invert the right qubit. So C naught. So I'm going to operate C naught. And this is, of course, the 1, 0 C naught, but I'll just write it as C naught from now on. Okay. That is, so now let's look at what C naught does to the superposition. Okay. So 0, 0, clearly unchanged. 1, 0, that has to be inverted, right? 1, 1, 0, 1, not changed, and 1, 1, inverted the right qubit. But this state and this state are identical, right? They're the same. So I know immediately this state can be written as plus times plus, right? And now it's very easy to understand action of Hadamard on this state. H, tensor H, acting on plus plus. What does that give? Anyone? What should it give you? Yes. 0, 0. Excellent. So we have our first truth table, or whatever you want to call it, for the LHAs, which is that 0, 0 remains 0, 0. Let's make sure on this side that that is also true. Okay. The left qubit is 0, right qubit is 0. Makes sense. Nothing happens to the left qubit. Right. So on the LHS, or the RHS, I'm going to agree, yes, 0, 0 indeed goes to 0, 0. Okay. Okay, now you see the pattern, right? So we have to start doing this for every combination. H acting on 0, 1, right? That's our next state in the 2 qubit space. Okay, well, H will give me plus. And what about this one? The second one? Yes?
Minus.
Minus. Okay, now we want to write this out. So 1/2. I'm just going to skip one step here. 0, 0 minus 0, 1 plus 1, 0 minus 1, 1. Okay. I'm just skipping a step there. Hopefully that's okay. Oh, I got this. Okay. So now C naught with the left qubit as the control and the right qubit as the target. C naught 1, 0 thing on this left on the state is going to give me 1/2 0, 0 minus 0, 1 plus 1, 1 minus 1, 0. Right? Flip the 1, 0 and 1, 1 states in that superposition. Now let's see if we can write this. It takes a little bit of staring at this to try and come up and see if there's a way to write this as a combination of plus and minus states. We can also, of course, just actually substitute for 0 as plus, minus, and 1 as plus, minus, and do the whole algebra, but it's simpler just to like stare at it and figure out what would work. Okay. I hate saying that, but it's kind of true in this case. Okay, let's see. I think it is 0. So I kind of write it as 1 over root 2, 0, 1 over root 2, 0 minus 1. Right? That's this first term over here. Okay. Plus 1 over minus 1 over root 2. Carry on. Times 1 over root 2. 0 minus 1. That's 1 over. It's 1 over 6. Everybody see this? I'm just trying to find common factors, basically. That will allow me to factorize this. Okay. That's, we just multiply it out on the here. This is 0, 0. Excuse me, 0, 1. Minus 1, 0 plus 1. Okay. Yeah, you
Why is there a subtraction sign?
here.
Yeah.
Because what I did was imagine that I factorize this out. Let's do it actually. So imagine I take out the 1, right? Because I see that the 1 is sitting in both of these first. Then I would get here 1 minus 0. But here I have a 0 minus 1. So if I want to factorize, I write this as a minus sign and then a 0 minus 1. That's all it is. And I take the root 2's because that makes it easy to see that everything is a combination over. Okay. So coming back here, continue writing this. That is the state plus times minus. No, sorry, that is minus and minus. Right? Because when I factorize out this guy to the right side, I'm left with 0 minus 1 on the left side. So that's a minus sign. Everybody okay with that? Not stop me, okay? Okay, you're fine. Okay. Okay, and now H, tensor H, acting on minus. What does that give? Yes?
Did 1, 1.
Very good. So our next term in this truth table is, we saw that H tensor H acting on 0, 0 gives me 0, 0. Okay. And we check the right hand side does the same thing. So we can say for this term it's satisfied. Okay. What about the right hand side acting on the 0, 1 state? What does that mean? Well, remember the right qubit is the target, is the control qubit in the right hand side of that equation. So that should give me 1, 1. And that is exactly what we just showed over here. So for this term as well, the identity is satisfied. Okay, 0, 1 goes to 1, 1. Okay, I think you get the pattern. 1, 0 as well. Let's do that. H tensor H acting on 1, 0 gives me plus, minus times plus, which if I write out, just 0, 0 minus 1, 0, 0 plus 0, 1 minus 1. T naught acting on this, give me 1/2, 0, 0 minus 1, 1 plus 0, 1 minus 1, 0. Okay. Actually, if you look at it, it's exactly the same that we wrote down here. Okay. Oh no, it is not. Yeah, it's different. Sorry. Okay. Anyway, we have to stare at it again. Figure out what we can factorize. It's 1 over root 2. Okay, let's try to factorize over here. Let's see. There's not anything I can factorize here. That's not possible. Let's see if I can factorize over here. Okay. So that's 0, 0 times. I mean, I have this written down in my notes, but I figured it'll help you to see that I'm struggling to factorize this. Not always trivial, but it's doable. At least for 2 cubes. So that's just this term and this term that I took out. Then here I can factorize the 1 And I want to have something that leaves me with a 0 plus 1 because that's what is here on this side. So I'm going to take minus 1 over root 2 times over root 2 0. Oh. Okay. That's this 1 here and 1 here. So when I take a minus 1, I'm left behind with 0 plus 1. Okay, so we can write this down as 1 over okay, so this is hopefully obvious 1 over root 2 0 plus 1 0 minus 1 2 sorry. Okay. 0 minus 1 over root 2 times 1 over root 2 0 plus 1. So this is the term minus times plus. Okay. And acting with Hadamard tensor, Hadamard gives me 1 0. Okay, let's look at our state over here. Okay. So if I have 1 0, the right qubit is 0 and the left qubit is 1, it does nothing to the left qubit. I get back 1 0. Which is exactly what I got. We have identified the third term in the identity is also correct. Are we following this? Okay, just the identity always takes me forever to prove. Why am I spending so much time on it? Because a lot of identities are often done this way, okay, to prove, to visualize what's happening. So this method that I'm teaching you is usually applicable to all the other types of identities that you might see. Okay, the last one, of course, we want H tensor H acting on the 1 1 state. That's going to give me minus and minus. Okay, and C naught acting on minus times minus. Well, let's write it out fully. 1 over root times 0 0 minus 1 0 plus 1 0 plus H. Okay, C naught acting on that. Give me 1 half 0 0 minus 1 1 minus 1 oh wait. I'm not seeing it. I have to just write it. Usually I can do it in my head. Okay, so the first term is 0 multiplying those two terms. 0, 0 minus 0. Okay, everything else is correct. The 0, 1 happens, and 1, 0 is inverted, minus 1, 1. The last term. Okay. You can see, you can took you. So, right. So again, let's try to find some common factors here and factorize this out. I think it's fairly straightforward because see the 0 here and the 0 here. So you get 1 over root 2 times 0 times 1 over root 2, 0 minus 1. Okay. Plus, or in this case, if I want, yeah, plus 1 times 2, of course, times 0 plus 1, 0 minus 1. Right, because you get a 1, 0 and a minus 1, 1, which is what is on this side. So that gives me at the final stage. Now, the last term in the identity. So we get, so this is just now plus times minus. So the C naught operation of C naught is just to give me plus times minus, right? Is that what I wrote? Yeah. Plus times minus, and Hadamard, tensor Hadamard on plus times minus gives me the output state 0, 1 or 0, 1. So I get 1, 1 state goes, Okay, well, I'm saying, sorry, I'm telling the right hand side gives me that. Now let's check the left hand side. Indeed, when the right qubit is 1, the left qubit flips to 0. That is indeed the action of the C naught gate with the control qubit on the right qubit and the target qubit as the left qubit. So all 4 terms have been verified. And if all 4 terms are verified, that means any general superposition that takes these inputs will give me those, and therefore the theorem is proved for all states that this identity must be. Any questions? Yes. You may have to go back and stare at it a couple of times if you're not sure, but or comment on me. Oh, and by the way, because we have shown the action on 0, 0, over here, back here, we can now write down the matrix representation for this C naught gate as well, right? Because as I just showed you, as soon as you know how C naught acts, you can write each of these as a column vector, and then the output of C naught can be written as another column vector, and then stack all those column vectors to give you the matrix representation for this new gate, C naught 0, 1. Okay. So C naught 0, 1 can also be written as a matrix, and you can, I can tell you that, this is what you'll get. So this is the proof using matrix multiplication. Okay. So again, if you stared at it though, this one looks a little bit weirder, right? Because it has 1, 0, 0, 0, that's fine. But then see that last one becomes a 1 over there, and this one is a 1, and this one is a 1. So it's harder to see that it can be thought of as a control X gate. That part is somewhat, there's an X gate over here maybe, but then these two are clearly, separated out. They don't look like an identity matrix anymore. So now we begin to see that the matrices, that we are getting are a little bit more complicated. It's harder to see them as like combinations of C and X and all that anymore. Okay, so anyway, just to show you, I just wrote down the C naught gate first. That's the C naught gate that we just introduced. Verified that it indeed gives me all those same column vectors that we did earlier in the class. And then all this is taking the LHS, right? LHS is Kronecker product of H and H times matrix multiplication of C naught times the Kronecker product of H and H. And I have to do a couple little things just to make the printing little more clean in Python, because Python operates with everything with floating point numbers. And so if you try this directly and you try to print it, it'll look very ugly. It'll be hard to compare with your clean answer that you get from doing it by hand. The reason is because Python, is working in floating point numbers, so there's like 10 to the minus 23 something, So of course that's 0. So I just set that to 0 with a couple lines of code. Just say that anything below 1 to the minus 6 is 0. Yes. And with that, then it clearly looks like the matrix that we just did. I can do this. I can write down the matrix here for you if you want, but I suggest you go back with this action that we just wrote down over here. Try to write the matrix just by looking at this truth table, so to speak. Write down the matrix for C naught 0, 1 on your own. Okay, and then you can make sure that it agrees with this matrix algebra version that I just wrote down. And to prove that it is indeed in matrix algebra, I operate with the LHS, which is, I just showed that the LHS and the RHS are equivalent. Then I act with that, I get, LHS on ket 0, 0, 0 is 1, 0, 0, 0, that will be the column vector 1, 0, 0, 0. Acting on 0, 1, which is the next state. When I was doing it, for some reason, I put 0, 1 in first. Then I get 0, 0, 0, 1, okay, which should be the second column over here, 0, 0, 0, 1. And then acting on the third, which is ket 1, 0, I get 0, 0, 1, 0. And that is this column over here, 0, 0, 1, 0. Then the last column is 0, 1, 0, 0. That is LHS acting on ket 1, 1 is 0, 1, 0, 0. Okay. So we can see that the action of this matrix on those basically reveals the same structure as here. The 0, 0 goes to 0, 0. 0, 1 goes to the last element, right? The last element here is, of course, the 1, 1 element. So that's why we get 0, 0, 0, 1, which is exactly what we have here. 0, 1 goes to 1, 1. Sorry, can you see this? I turned on the lights and so on and so forth. Okay, I'm going to stop there for today. See, we have not completed at all. I hope to. That's fine. We'll start in the next class. Control U game. Okay. Well, all right. Have a great break, everyone. I'll see you all afterwards.